Morning, everyone. How are y'all doing? It's a great day today, isn't it? Oh, I see my usual crew over on YouTube. Good to see you today. Well, today, sorry, I'm still setting up my computer here. That's why I'm looking down. Today, we're going to continue where we left off last time. I think the last thing we were doing last time was the Totient function, if I have my memory correct. Oh, I'm doing pretty good today. Thanks for asking. I didn't actually get much sleep last night. I was up until 1:30 in the morning getting today's programming assignment done. You know, I actually had the primary assignments done, a couple of years ago, and I've just been refining them ever since. But last night I was like, I really just need to rework this. It doesn't flow, I think, very well. There's 4 pages to it. So I don't think the individual pages flow very well. So I was up copying and pasting in the Python notebooks for hours to try to get everything in the correct order again. So so I was up pretty late last night, and then had to get up early, usual time, to get the kids off to school. So not as much sleep last night as I usually get. I think actually I want to start us off with a video today. If I can get that set up. So you may have, if you follow the math headlines like I do, once in a while somebody comes up with the largest prime number that's been found so far. Now you probably know there's an infinite number of primes, so it's just a matter of finding the next one. And they're getting bigger and bigger and bigger. Currently if you print primes out, they come out to be just hundreds of pages long. You just print them out, with all the digits on them. And so they're fairly large. And so it's getting harder and harder to find the next one just because of all the checking that has to be done. You basically, naively, you can find a prime by trying all of its possible factors, but there are easier ways to do it. There are faster ways to find prime numbers. It still involves a lot of calculations, but this video is going to show you how they find prime numbers. Okay, so let me get that going, and then I'll be back in, let's see, how long is this video? It's about 12 minutes long, so we'll be back in about 12 minutes or so.
If you want to check a normal number if it's prime, a small one, you just see if any numbers divide into it. You can get slightly smarter. You've only got to check if primes divide into it, and you've only got to check if primes up to the size of the square root of the number you're checking or not. And so there's a few shortcuts you can make. This number, however, when you're finding something, look at the size of this thing, right? There's no way you could just go through and check every conceivable prime factor of this number to see if it itself is prime. In fact, there's a much more clever way of doing it. Well, I have successfully divided it by 3, so I don't know if that, technically doesn't count as I've taken a prime and I've split it into 3 parts, albeit not 3 equal parts. If anyone's curious, it's 1,490 pages, but I double-sided them, so it's about 250 pages of volume. Okay, you want to find primes. Previously, I showed you the Lucas numbers, which I prefer to Fibonacci numbers. These are the vastly superior Lucas numbers. They start with 1 and 3 instead of 1, 1 Fibonacci, and then they carry on exactly the same. You get 4, you get 7, you get 11. I need to make sure I get this correct, otherwise it will be very, very embarrassing. And what's that going to be? 47. So there's the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So Brady, can you give me any number 1 to 10 inclusive? What would you like? Anything 1 to 9, 1 to 10? What do you want?
5.
5. Okay, so we're going to see if 5 is prime. Now, a lot of people at home, because the people who watch Number File tend to be into mathematics, know 5 is prime. Spoiler. But let's say we don't know. Say, I don't know if 5's prime or not. Let's double check. I'm going to count along to the 5th Lucas number. 1, 2, 3, 4, 5. I'm going to subtract 1 off that number. And if I subtract 1, I get 10. And then I check, is 10 a multiple of 5? And it is. And because 10 is 2 times 5, 10 is a multiple of 5, I know 5 is a prime number.
What?
Probably.
Oh.
So, okay. So give me another number that's not prime. Just,
6.
6. I wonder if 6 is prime. Let's check 6. 1, 2, 3, 4, 5, 6. Take 1 off. 17. 17 is not a multiple of 6. 6 is not prime, and 6 is definitely not prime. And so this Lucas test, it will rule out a number that's not prime. So you can comprehensively prove a number is not prime by using this test, even though you don't know what any of the factors are. If it does pass, then we call it a Lucas pseudo-prime. It's very likely it's going to be prime, but it's not guaranteed at this point. So this is a very easy test. It's a good first filter to check if a number is prime or not, and you don't even have to look at its factors. So for a number this big, first of all, we need something a little bit more clever, and secondly, we want to be sure, right? So we want a similar test which guarantees it definitely is prime if we find it, and that's what we're going to do now. Right, for the big fellas, we need a different sequence, and again, it's our friend Lucas, what a guy, what a mathematician, and a guy called Lima, who we never met because he lived much later after him, and he was French and American, but together they came up with this method which uses the following sequence. You start with 4 this time, and then after that you square the previous number and subtract 2. So 4 squared is 16, 16 subtract 2 is 14. And then we do the same thing. We square 14, we subtract 2, and you get 194. You then square 194, subtract 2, you get 37,634. They get big very quickly, so the next one's a bit of a monster. So you go from 37,000 something up here to 1,416,317,954. And then now you can see what's going to happen. We're about to square this guy. They're getting roughly twice as long each time. The next number, hold on, is 2 billion. It escalates very quickly, and you end up with some massive numbers in there. And so actually it becomes incredibly very unwieldy very quickly to do anything with it. We'll fix that problem in a moment. Let's start by proving a number is prime. We're going to use a small Mersenne prime on this sequence to start with. I'm going to use 7 because it is 1 less than 2 cubed. So the way you check a Mersenne prime against this list is you take the power, which for 7 is 3, you subtract 1 off that, which is 2, and you find what's in the second position in the list. So the second number is 14, and you see if that is a multiple of the number you're checking, 7. And it is, look at that. So 14 is a multiple of 7, so 7 is definitely prime. Let's recap on that very quickly. If you've got 2 to some p prime power there minus 1, and that equals some mystery number, if the p minus 1th position in this sequence is a multiple of that number is definitely prime. And there's no ifs or buts or maybes. We know it is absolutely prime. And if it's not a multiple of that number, it's definitely not prime. And so this is a primality test. You can check if a number is prime or not, and you never have to look at its factors. This is what Lucas used. He managed to prove that 2 to the 127 minus 1 is definitely prime by finding the 126th term in this sequence and proving it was a multiple of that massive number that come out the other side. He also amazingly managed to prove that 2 to the 67 minus 1 is not prime. But he never found a single factor for that number. he was able to prove this is not prime without finding a number that divides into it. I think that was it was much later on, decades later, someone actually found what the factors were. We knew they were there, we just didn't know what they were, but we knew it wasn't prime. That prime is actually the biggest prime that was found by hand. All primes after that have been done by computer. So to check this number here, what we would have to do is continue this sequence, find the 74,207,280th position, and check if it was a multiple of this monstrosity. Now that actually is going to take a ridiculous amount of computing power. You can see how big these numbers get. They're going to get ludicrously large, and so actually that is not a good way to go about it. Let's make our life easy. Because when you're searching through for this guy here, all you care is whether or not the 74,207,280th position is a multiple of it or not. All you really want to know are the remainders once you've divided by this number. And so as you go along, you don't have to keep track of the entire Lucas-Lima sequence. You just need to keep track of the remainder mod this number as you go along. So you can keep simplifying it down each step of the way. And we can do a quick example if you want to show how that works. One of my absolute favorite Mersenne primes is 8,191, which is 2 to the 13 subtract 1. And so to check this number, we would have to find the 12th term in the Lucas-Lima sequence, but we only have to find it mod 8191. So to start with, it's the same. You'd have 4, you'd square that, you'd get 14, you'd square that, you'd get 194. Let's get these right. Then the next number should be 37,634, but that's bigger than the number we care about. And so actually we need the remainder of that number once we've divided through this number. In that case, it's only 4,870. That's easier. And then we square that, subtract 2, get the remainder once we remove multiples of the number we care about, and you end up with 3,953 followed by 5,970, and you can see this time these are staying much more manageable in size. Okay, then 128, and then the 12th term is 0. If you square that, subtract 2, you get a multiple of 8,191, and because that's 0, there's no remainder, we know whatever that massive ridiculous number should have been in the sequence, it's definitely a multiple of 8,191, therefore that is definitely prime, and we didn't have to check a single factor of that number. Okay, and so this is what the computer at the University of Missouri did, although obviously it does a slightly more efficient version of this, and there's some nice things you can do with the way it handles the binary versions of these numbers. Anyway, it's a fancy version of going along this sequence, finding the result modulo this ridiculous number, but you can do that just by subtracting it off until you get a number smaller than it, so that's not so bad. Once it got to that position, it looked at the answer, there was no remainder, and normally there's a remainder. The vast majority of the times you'll check a number of this size, spend a month on it, the computer will get to the end and go, oh, there's a remainder. Well, it's a computer, it's got no emotions. It would just send back the remainder to the central server. On this occasion, it was 0. The computer had no idea what it had done. It sent that off back to the central server, and that was it. We had found the biggest prime number known to humankind. So the problem is, this method only works for Mersenne primes. But actually, the trouble is, every single time you do it, it's a month of processing work, right? And so you think, how many, I mean, this is millions and millions of months. But obviously, we only have to check the way Mersenne primes work, and there are some fantastic number of our videos on Mersenne primes, you only got to worry about prime values up here. And so once, if this hadn't been prime, if that had not worked, the next one checked would have been the next prime up after this. And so we're gradually ticking up through those primes. You're right. In the bigger scheme of things, there aren't that many, but it's a month every time you want to check one. So, I mean, definitely everyone download GIMPs, the computer program, and run it, and maybe you'll be the person who finds the next one of these.
Matt, if they put some of the world's more high-powered computers onto the case here for like a few months, would they burn through this? Like, is it silly that we're just using little small computers in universities?
Yeah, no, it's a very good point. If we did have a big high-powered computer, like if Google went, you know what, guys, borrow the server. You know what, I reckon if Google really wanted to, they could just go and find the next one. If they just, everyone stopped searching for a day, we've got something to do with our computers. But then again, I mean, what are they going to achieve? They're going to find a bigger one, and then everyone's like, oh, okay, and start searching for the next one. I mean, the point of this is kind of the hunt. And the fact that thousands of people run the program, and any one of those people could find the next one. That, for me, is the beauty of the project. It could be anyone sitting at home running their computer could make a substantial find like this. They could contribute something to mathematics, and for all of eternity, you would be the human that found that prime number.
What would it mean to you if your computer found the next big one?
Oh my goodness, I would be so excited if I found the next. I would absolutely love to find it. I mean, very small confession, I don't run GIMPs on my computer. I run a competing prime number searching outfit called PrimeGrid. And so PrimeGrid searches for other types of primes. So look for like domain primes and other ones. And so currently GIMPs have the top 15 biggest primes. They found them all. PrimeGrid, it's a lot less likely you'll find a prime, which is a bit sad for me. But if they do find one in a few categories, they're going to come in at something crazy big. And so I play for the underdog. So I support PrimeGrid because I like the fact they're doing different types. I mean, these GIMPs guys are just in it for the glory. They're just going for the low-hanging, easy, big ones. They're just picking them off one after the other and getting all the recognition. But, you know, I like the fact that as we speak, at home, my computer is doing maths, so I don't have to. The question everyone has is always, what does it begin and end with? Ending, I don't find, everyone loves the last number. But the trouble with the last number is you know it's not going to be an even number. You know it's not going to be a 5. You know it's not going to be a 0. Turns out it's a 1. There it is.
I love that video because it, you know, Matt Parker is just so excited about the topic. And also, what more appropriate than the stuff we're talking about these days in our current classes, because it combines modular arithmetic and you know, sequences of numbers, a recursive sequence where each number in the sequence is calculated from previous numbers in the sequence. And I said in the chat that we'd review these sequences right after the video ends. So let's go over some of the terms that you probably heard in that video. So one of them was the Fibonacci sequence, and I hope you've heard about this sequence of numbers. In that sequence, every number in the sequence is calculated by summing up the previous two numbers. So for example, 8 here is found by summing 3 and 5, and 13 is found by summing 5 and 8. So you start with the first two numbers, 1 and 1, and then from there you can build out the rest of the sequence. So we can write a function that will calculate the nth number in the sequence fairly easily. Let me number them. This is 1, 2, 3, 4, 5, 6, 7, 8. So we could calculate, let's say, the 7th number in the sequence by calculating the 6th and the 5th numbers. And from those, we can just add them together and get the 7th number. So here's what the definition by parts would look like. Make a function called fib, short for Fibonacci, and we want to know the nth number in the sequence. And so the nth number is 1 if n is equal to 1 or 2. So if n is 1 or 2, the answer is just 1. Those are your base numbers. You're just given those numbers. And then for all other values of n, it's equal to the Fibonacci, the n minus 1th number plus the n minus 2 number otherwise. Okay, so if n is 1 or 2, the answer is just 1. If n is anything else, then you calculate the n minus 1 number in the sequence and add it to the n minus 2 number in the sequence, and that gives you the current number. And we can actually do this in Python fairly easily. We can say define fib n, and say if n is equal to 1 or n is equal to 2, then just return 1. Else, return fib of n minus 1 plus fib of n minus 2. And then we'll try it out. What's the 7th number? It's 13. What's the 10th number? 55. So this particular function doesn't generate the whole sequence. It just generates one number in the sequence. 15th number is 610. Another sequence that was discussed in the video was the Lucas numbers, and these are calculated the same way as the Fibonacci numbers. You just start with a different set of starting numbers. So instead of 1 and 1, you start with 1 and 3, but otherwise the calculation is the same. And then finally there were the Lucas-Lemur numbers, and these are the ones that grew really big very quickly. And the formula for that one is, we'll do Lucas-Lemur of n. This is the nth Lucas-Lemur number, is equal to 4 if n is equal to 1. And it's equal to the previous number squared minus 2 otherwise. So during today's programming section of the session, we will actually write the Lucas-Lemur number functions to be able to calculate those numbers. And you'll see how they grow very big, very quickly. But we'll use this definition by parts, and we'll turn that into some Python code to do that. Also mentioned in the video was Mersenne primes. And Mersenne primes always take the form of 2 to some prime power minus 1. For example, the third Mersenne prime is 7, and the 13th one is 8191. Those were two of the ones that were shown in the video. Oh, and then also he mentioned that, who was it, Lucas or Lemur? One of those two mathematicians was able to show that this Mersenne prime, 2 to the 127th minus 1, which is this really big number, was shown to be prime. And remember that this person did that entirely by hand. So, you know, imagine trying to find, you know, the 126th term in that sequence and seeing whether it's a multiple of this number and doing that entirely by hand. So, a lot of work there. So any questions, comments about that video that we saw?
What was like the purpose of finding primes like before encryption? Like, what is it, just like a mathematical like flex back then?
Yeah, yeah, pretty much. And it really does kind of drive research into working with numbers more and more efficiently, because as these prime numbers get bigger and bigger, we need to find faster and faster ways of doing it. Sure, you could throw more computing power at it, but you know, computing power, they say, only doubles every 18 months to 24 months, but the primes are getting bigger, you know, much faster than that. So you can't just simply throw more computing power at it. You now need to come up with faster and faster ways to do it. And so it is really, you know, primes are useful for things like cryptography. They're also useful in other areas, but yeah, like you said, finding primes is more like just bragging rights, pretty much. Nevertheless, all the number theory that's come out of it has really been helpful in other areas, because when you work with cryptography, you need to generate prime numbers, and you need to be able to do that fairly quickly. Just testing all the factors of a large number is going to take forever. If you can do it quickly, then you know, you got a big win there. And so actually, when your browsers connect to a web server and then you get that little lock icon, it has to pick some prime numbers to kind of seed the whole encryption routine. It has to do it quickly. So there are primality tests out there that'll test to see if a number is prime or not really quickly. For largish numbers, but not huge numbers. You don't necessarily need huge numbers. You just need largish numbers, like 20, 30 digits. And you can test those pretty quickly. And some of these primality tests, interestingly enough, are just what are called probabilistic, which means they come up with an answer, kind of like in the video, they said, this number is probably prime. We're 99% sure it's prime. We can be 100% sure if we actually check all its factors, but we can be pretty sure if we do this quick and easy test. You've probably actually done kind of an informal primality test yourself. You might look at a number and go like, well, it's not even, right? And it's not a multiple of 10, it's not a multiple of 5, so it's probably a prime, right? And you might try a few factors. You're like, well, it's not a multiple of 5, it's not a multiple of 7, it's not a multiple of 11 or 13. You know, that just right there, that probably eliminates 90% of them. Right there, right? Factors of fairly low numbers. So you yourself have probably done some really quick primality tests just to see whether a number is probably prime. Once you arrive at the answer is probably prime, then maybe it needs a little more investigation. But if you can just eliminate it off the bat and say this is definitely not prime, then you don't have to go any further, right? So when we left off last time, we were talking about this totient function. And we had informally said that it's the number of numbers that are co-prime to n and less than n. Let me put that in there. And less than n. And bigger than 1. So the totient of 11, how many numbers are less than 11 and co-prime with 11? What did we come up with there? Now this one was easy. Right? 11 is prime. So how many numbers less than 11 are co-prime with it? Share no common factors. Well, 11 doesn't have any factors other than itself. So this was just 10. It's easy to do. You just subtract 1 from the number and you've got the number of factors. You've got the number of numbers that are co-prime to a prime number. What about 15? 15 is a composite number. It's not prime, so we can't do the easy just subtract 1 from it. So there was another property of this that says if the number is composed of 2 prime factors and those factors are different from each other, then you can break apart the number into its prime factors, find the totient of each one of those factors, and then just multiply those together. So this can be split up into the totient of 5 times the totient, oh, I'm getting sloppy here, times the totient of 3. And each one of those are prime. So we get 5 minus 1 times 3 minus 1. And that is, what, 4 times 2, which is 8. And then finally, 125 has 3 factors, 5, 5, and 5. But since they're not different from each other, you can't use the property right above. You have to use a different property. And so the property for this one is to calculate the totient of a prime raised to a power. This is p to the nth power, we'll say. Then it is p minus 1 times p to the n minus 1. So we've got 5 minus 1 times 5 to the 3 minus 1, which is 4 times 5 squared, and that's 100. So that's where we left off last time. What we're eventually working our way up to is how can we use this to help us decrypt the linear cipher. So the linear cipher formula is the ciphertext is equal to the plain text times a multiplier plus a constant. all mod n. So if we solve for p, if we want to decrypt, we can do p equals c minus k, divide by m, and mod n. But the problem here was we end up with a fraction. And so the solution to that is, instead of dividing by m, we are going to multiply by its multiplicative inverse. When I say m to the negative 1 power, anything to the negative 1 power, that means this is the multiplicative inverse of m mod n. So instead of dividing by m, which gives us a fraction, we're going to multiply by its inverse. Last time we encrypted the word music, and we came up with these 5 numbers to represent those 5 letters. We also used m was 5 and k was 7. So we encrypted the word and came up with PDTVR and these numbers. And now we want to reverse that. We want to go backwards. So if I decrypt P, I should get M. If I decrypt R, I should get C. I want to be able to reverse this calculation. And that's what we're going to do right here. So let's go. P is equal to, let's tackle the first letter right here, 15. 15 minus k, which is 7. Okay, so here's this 15 right here. Here's the 7 right here. And now we need to multiply it by m to the negative 1 power mod 26. So we need to calculate this number. Remember, the multiplicative inverse is the number which, when multiplied by another number, gives us 1. So we need to find a number which, when multiplied by 5, gives us 1 in mod 26 counting. So 5 times, let's call this, well, let me back up here. M times m to the negative 1 should be equal to 1 mod 26. So this is 5, m is 5. What's m to the negative 1 power? And last time, we discovered that we could just write a loop, basically, just goes through and tries all the possible numbers until it stumbles across the one that happens to work. I'll use A here. So we'll go for B in range 1 comma n. If A times B mod n is equal to 1, then we'll return B. That's the answer. And assuming there is a multiplicative inverse, which there will be if m was chosen well. Remember, you don't want to pick a number that's not co-prime with n. So you're guaranteed to find a multiplicative inverse. But if not, we could say something like return none if we get all the way through the loop and we didn't find any. So let's plug in 5 and 26, and it comes up with 21. So 21 times 5 mod 26 will give us a remainder of 1. let's take that number and plug that in over here. All right, so 15 minus 7 is 8, and then 8 times 21 is 168, and then 168 mod 26 is 12. Okay, I can run that calculation all together instead of one at a time. Okay, so we get 12 out of that calculation. And is that correct? Is 12 what we're looking for? Let's see. So we plugged 15. 15 was our ciphertext, and we want to reverse this calculation. And sure enough, we end up with 12. Let's try it again, just to make sure that wasn't a complete coincidence. Let's do p is equal to, let's tackle maybe the last number in this sequence, 17. Still using the same multiplicative inverse, so that hasn't changed. Now we're going to do 17 minus 7 times 21. Mod 26. So let's run that calculation. 17 minus 7 times 8. Oops, times 21. Is that right? Now I'm looking at this going, why did I multiply this by 8? That should have been 21. Still end up with 12. Mod 26, and we end up with 2. Okay, so 2 is the answer we're looking for right there. 17, work it backwards, you get 2. That's what we got here. So that's what we're aiming for here, is a way to decrypt the linear cipher by eliminating the division and instead multiplying. Remember, the modular arithmetic kind of like is on a wheel, and when you multiply, you just go several times around the wheel. So what we're doing here is, subtracting is easy, right? You just go the other direction. So we're going to subtract, we're going to start with a plain text, we're going to go around the wheel a few times, and then add a little offset, and we end up over here. And then to come up with the plain text from the ciphertext, we're going to subtract off that offset, but then instead of dividing, we're just going to go around the wheel some more times. And then when we do that, we end up boop, right where we started. Okay, but we wrote a function to find the multiplicative inverse by running a loop. And if a and n are both large, particularly if n is large, it could take a while to run that loop. We're trying basically every possible number until we stumble across the one that happens to work. There's got to be a faster way to do it, and in fact there is. So this was where Euler's theorem comes into play. This is another one of those things that was thought about hundreds of years ago. Probably wasn't that useful when it was created, but now these days it is, because now we have to find things like multiplicative inverses quickly in order to be able to decrypt. And it's not just a simple cipher like the linear cipher. Even complicated ones like RSA, the ones that are currently used for modern browsers, still have to find the multiplicative inverse in order to be able to decrypt. So we got to be able to calculate this thing quickly, and we got to be able to, it's got to be able to work with large numbers. So here's Euler's theorem. Euler's theorem is, you've got some number a raised to the totient of n, and that's going to be a 1 mod n if a and n are both coprime. Okay, so if a and n are coprime to each other, then this equation holds. So it turns out Euler's theorem is incredibly useful, but not in its current form. We got to do a little bit of work to it to make it really useful. So I'm going to divide both sides by a. And I get a to the totient of n divided by a is equal to 1 over a mod n. But let's rewrite that without the division in there, because remember, division kind of poses a problem. I can take care of the division on the left side by just subtracting 1 off of the exponent. And I can take care of the division on the right side by just rewriting it as a to the negative 1 power. But this gives us what we want. This is a really powerful result because a to the negative 1 power mod n is the multiplicative inverse of a mod n. So in other words, to find the multiplicative inverse of some number a mod n, all we have to do is calculate the totient, raise it to a power, and we've got it. So we don't have to try all the possible numbers and stumble across the answer. We've got a direct calculation. Plug the numbers in, boom, there's your answer. Let's try it out. So let's do 5 mod 26, which was the number that we were calculating on the previous slide. We know the answer is going to be 21 because we did it using the loop, but let's try it using this more direct method. So a is going to be 5 and n is going to be 26. So we need to solve 5. Oh, well, let me write it this way here. 5 to the negative 1 power mod 26 is equal to, so that's, I'm basically taking this equation here and just flipping the sides. So here's 5 to the negative 1 power is equal to 5 to the totient of 26 minus 1. Mod 26. All we have to do is calculate this number, totient of 26. All right, so totient of 26. Let's see, 26 is composite, but it can be split up into what factors?
13 and 2.
Good, 13 and 2. And then since those are both prime, we've got 2 minus 1 times 13 minus 1, which is 12. Okay, we're halfway there. This 12 is the answer to this here. Now we just have to do 5 to the 12th minus 1. Mod 26. So this is 5 to the 11th power. Mod 26. And 5 to the 11th power is, oh, that humongous thing, 4, 8, 8, 2, 8, 1, 2, 5. But we're just going to do a mod 26 at the end. And we get 21, which is exactly the answer we're looking for. Okay, Akash asks, is it possible to calculate the totient function quickly without doing prime factorization? So that's a really good observation there, that in order to be able to calculate this totient number here, I had to factor it into 2 and 13. And for large numbers, that's actually difficult to do. So you're right. This, although this gives us a direct calculation for finding the totient, it's not super direct because prime factorization is not easy to do. So we need another way to do this. But nevertheless, I wanted to show you that all this stuff ties in together. This totient stuff and Euler's theorem and finding multiplicative inverses that way. And we will come back to these things. These things still are useful, even though it's not the super fast way to find the multiplicative inverse. There is another way to do it that's faster. But it's still useful because when we do RSA next week, we're still going to need the totient. We're still going to need the multiplicative inverse. So it's not like we are just going to learn this stuff and then set it aside. Still need this. All right, so let's just quickly run through how would a little tiny send and receive of some text using the linear cipher go for a sender and a recipient. So let's say the sender wants to encrypt OK, which is 14 and 10, and M and K are 7 and 6. Those are the secret key that have been chosen by the sender and recipient. So to encrypt, we're going to go 14 times 7 plus 6, and 10 times 7 plus 6. Do those both mod 26. Let's see, 14 times 7 plus 6 is 104. And then 104 mod 26 is 0. And then 10 times 7 plus 6 is 76. And 76 mod 26 is 24. So we could convert those into letters. That would be A and Y, AY. And that's what you would send to your recipient. Okay, so your recipient converts those back into numbers, 0 and 24. And then your recipient is doing P equals C minus K times the multiplicative inverse, mod 26. So your recipient is going to do 0 minus K, which is 6. And then you're going to multiply it by the multiplicative inverse. So we're going to go off to the side here, and we're going to calculate. Multiplicative inverse of 7 mod 26. Okay, so remember, we're going to calculate a to the totient of 26 minus 1. So we've got 7 to the totient of 26 minus 1. And we already calculated that the totient of 26 was 10. Was that right, or was it 12? Let me look on the back slide over here. It was, totient of 26 was 12. So you got 7 to the 12th minus 1. 7 to the 11th. Let's see, 7 to the 11th power is this huge number. But then if we do that, mod 26, then we get 15. Okay, so we'll take that number 15, we'll plug that in over here. Okay, 0 minus 6 is negative 6 times 15 mod 26. But we don't really have to do negative 6. We could find its congruent number. That would be 20, I believe, if we're doing mod 26. So negative 6, let's try this, negative 6 mod 26 is 20. So that is its positive congruent number. $20 times 15 is 300. And 300 mod 26 is 14. And 14 is the number we're looking for. So we decrypted our 0 and got back 14. And we do the same thing for what did we get here? The 24. We'll plug 24 in right here, do the calculation, and we should get back 10. In fact, let's go ahead and we'll do that right over here off to the side. We'll do 24 minus 6 times 15. That gives us 18 times 15. Let's see, 18 times 15 is 270. And then 270 mod 26 is 10. And that's the number we're looking for right up there. Okay, so that's basically the process that the sender and recipient would do to encrypt and decrypt using this really simple linear cipher, but it does put together all the concepts that we've been learning over the past couple of days. So I said a few minutes ago that the problem with using Euler's theorem is you need to be able to factor the number into its prime factors in order to apply the totient properties. And that's kind of slow. We need a faster way. Last time, if you remember, we talked about the Euclidean algorithm for calculating the greatest common divisor. Oh, you're right. So doesn't the fact that the length of the ciphertext is 2 give some clue that's probably like okay or no or something like that? Oh, sure. But this was just an example of the calculations that need to be done in order to encrypt and decrypt. And really, no person using the linear cipher, and no one would be crazy enough to do that these days, but anyone who is using the linear cipher probably shouldn't be doing it letter by letter. If you do it letter by letter, then you still end up with ciphertext that is subject to statistical analysis, and then you can look at the most common letters and figure out what those are. Those are likely to be spaces or N's or T's or E's. And then from there, you can start guessing what other letters are. So most likely, if you're encrypting a large amount of text, large meaning more than just a couple of characters, you're going to split that text up maybe into groups of 4, 5, or 6 characters at a time, and then scrunch all the bits for those letters together and create like 40, 50, 60-bit numbers, and then you'll encrypt those. And that makes it much harder for your adversary to decrypt it, because now the numbers are just much larger to begin with. There's more possibilities to try out. If you want to guess what the M and the K are supposed to be, and remember, the M and the K should be roughly on the order of the size of the numbers that you're encrypting. So we're not just dealing with, although we're dealing with just 26 letters of the alphabet, we're dealing in blocks of, let's say, 4, 5, or 6 characters. And now it's not going to be mod 26. It's going to be mod 26 to the 6th power, which is a much bigger number. Like, here's that number down here at the bottom. And so M and K could be anywhere in that range. So there's a lot more things to try out. Still, for a modern computer, it's going to be able to whip through all the possibilities really quickly. So linear cipher is, of course, not something you would use for real encryption to do like banking or, whatever, any secret messages. You wouldn't, of course, use linear cipher. You'd use something more complicated and more secure, but the concepts are all the same. Okay, so going back to the Euclidean algorithm for calculating the greatest common divisor. If you don't remember that one, you'll have to go back to the video from last time, and you'll be able to review that. Also, we will review it coming up when we talk about the programming assignments for this week. But there is another thing called the extended Euclidean algorithm. It still works with greatest common divisor, but instead of coming up with the one answer, like the one number that is the greatest common divisor, the extended one is a more general purpose equation that comes up with 2 answers. And so what this equation is telling us is basically, given the values of A and B, it will return to you, it will solve for X and Y. Let me write that down. Given A and B, solve for X and Y. So last time we did some greatest common divisor examples using numbers like 30 and 90. Now we know the greatest common divisor of 30 and 90 is 30. So let's plug those values in for A and B and see what it comes up with for X and Y. So we've got 30x plus 90y is equal to the greatest common divisor of 30 and 90. Now we know that that is 30. It's the largest number that divides into both 30 and 90. So we have 30x equals 30x plus 90y equals 30. We can simplify this into x plus 3y is equal to 1. And now we just have to solve for x and y. And here's where you may kind of take a moment to say, whoa, what's going on here? When I took my math class, my algebra class, I learned that if you have an equation of 2 variables, you need at least 2 equations to be able to solve for x and y. But here we only have 1 equation with 2 variables. So that either means that there is just some unique combination of x and y that happens to work, or it means there's multiple solutions. So can you come up with values for x and y that satisfy this equation. Now, since we're adding the numbers together and we end up with a positive result, it's going to suggest to you that one of those numbers, either x or y, should be negative. Can you come up with values for x and y so that it satisfies this equation? So 3 and 1. So if I plug in 3 here and 1 here, I get not 1. Let's try again. How about 4 and negative 1? Let's try that. 4 and negative 1. So let's see. 4 plus 3 times negative 1, which is a negative 3. So 4 plus negative 3 is, in fact, 1. So this is a good solution. Avoid solutions that involve fractions. We just want to come up with integer solutions that work. Any others? How about x equals negative 2 and y equals 1? So we get negative 2 plus 3 is 1. So that works. Here's another one. X is 10, y is negative 3. 10 plus negative 9 is 1. So you see, with this particular equation, there can be multiple solutions that work. Now, turns out that one of these solutions is like better than the others. I'd probably pick this one, or maybe even this one, the second one. Maybe not the third one, just because this number is large. But any one of these solutions will work. But let's try this again with some different numbers. Let's try a is 3 and b is 26. Actually, let's not do a is 3. Let's switch this around for a is 5. Okay. That'll match one of the problems we did earlier today. Okay, so we get 5x plus 26y is equal to the greatest common divisor of 5 and 26. Now, 5 and 26 don't have any common factors. 5 is prime, and 26 is composite, but its factors are 2 and 13. So there's actually no greatest common divisor other than 1. So we know that the answer to the right-hand side is just 1. Now we just need to come up with solutions to 5x plus 26y equals 1. Can we come up with something that works? 5 and negative 1. Let's see. X equals 5, y is equal to negative 1. So this is 25 here. And this would be negative 26. So 25 plus negative 26 would be negative 1. So we're almost there. Oh, how about negative 5 and 1? Okay, just had the sign switched around. Let's try that. Negative 5 and 1. So now we end up with negative 25 plus 26, and that works. Any others? Can you come up with another set of numbers? This is a stumper, right? You could try some other numbers. How about x is 21? What value of y would work? -4. Good. Ravi's come up with the answer. -4. Okay, so 21 times 5 is 105, and -4 times 26 is 104, -104. So 105 plus -104 gives us 1. So that solution works as well. And so it turns out that this one here, x is 21, is actually really useful to us. X, the value of x, is the solution to calculate the multiplicative inverse of A mod n. Okay, so what you do is you plug in A right here, you plug in n right here, you solve this equation for x and y, and whatever you come up with for x is going to be the answer. You throw away y, you don't need that one. And the reason why I chose 21 here is because 21 mod 26 is the same as -5 mod 26. Those are congruent numbers to each other. So we've got 5 here, which corresponds with the problem that we did, oh, where was it? Way back over here. And we used 5 as our multiplier. And then later on, we did this one here, where our multiplier was 7, and we came up with 15 as being the multiplicative inverse. So let's see if we can plug 7 and 26 into this extended Euclidean and come up with the same answer. Let's do A is 7 and B is 26. 7x plus 26y is the greatest common divisor of 7 and 26. Now, this is just 1 because 7 and 26 don't share any common factors. And we're going to guess that x equals 15 works because we kind of already know the answer to this. What's the value of y? What value of y would work to satisfy this equation? -4. So 15 times 7 plus 26 times -4 should give us 1. And that is the answer we're looking for. Okay, but still, it seems like this, well, let me back up. The extended Euclidean algorithm gives us a more direct way of calculating the multiplicative inverse because we don't have to take a number and factor it into its primes. We can very quickly find the answer to the greatest common divisor by just using the Euclidean algorithm. We know that that's a very fast way to find the GCD of two numbers. All we then need to do is find these values for x and y. And what we did here is we just kind of did guess and check, right? We tried a value for x and see if it will work, try another value, see if it will work, and actually try values for x and y. But we need a more direct way to calculate that. And there does happen to be a faster way to calculate it. It is very similar to the Euclidean algorithm in that it's a recursive algorithm that calculates the values for x and y, and it does so in just a few number of steps. No more guess and check. It's able to just very quickly, directly calculate that number. We're going to go over that when we talk about the programming assignments for this week. So, what did we do so far in the last hour? Or so. So we learned about, gosh, what did we start with? We started watching that video about how prime numbers are found. And the reason why I showed you that video was because it involves things like recursive functions, modular arithmetic. The Euclidean algorithm is a recursive function. And of course, it uses some modular arithmetic. So there's a tie-in there. Then we started talking about the Totient function, which was a continuation from last time. And we do need that Totient function because it is used for not only curiosity, but also it's used in modern cryptography like RSA in order to calculate some of the secret keys that are used to encrypt and decrypt. And then we talked about the multiplicative inverse and some various ways to calculate the multiplicative inverse. We talked about Euler's theorem, which is very nice and very clean, but is not a direct way to calculate the multiplicative inverse because it involves finding the Totient, and the Totient involves doing prime factorization, which is slow for large numbers. And then we ended up with the Euclidean, extended Euclidean algorithm, which also can find the multiplicative inverse. It gives you two solutions. You throw away one of them, and the other one, the first one, the value for x, is the one that you're looking for. This one doesn't require prime factorizations, but as shown on the slides, it does require just sort of guess and check or running some loops to try various combinations of x and y until you stumble across the one that happens to work. And so when we come back from a break, I'm going to show you how to do the extended Euclidean algorithm, but with a recursive function that can find the answer really quickly. And it doesn't have to do guess and check. Okay? So we are going to take about, I know I threw a lot of stuff at you today, but we're going to put all those pieces together when we do our programming assignment for this week. So we'll take about a 10-minute break to digest all of the stuff that we just went over, and then we'll talk about the assignment. Okay?
Recording stopped.
Okay, so I can pause the Zoom recording, but I can't pause the YouTube recording. So you and I get to just hang out for about 10 minutes. And I can answer some of the questions you've been posing here. So one of the questions was, Whistleblower says, is the C Makefiles series completed or more videos coming soon? Are you talking about the one that's on YouTube already? My giant, like 55-minute video? I'm pretty much done with that video. There was a suggestion to maybe break it up into smaller pieces, which I could do at some point. But in my C class, which is Tuesdays and Thursdays at 9:30, we will kind of go over Makefiles again. It's coming up, I'd say maybe in 2 or 3 weeks when we do that. So not super immediately, but it is kind of just a rehash of the content of that long video. I've just not had time lately to do some of these shorter videos, shorter tutorial videos. I'm just, you know, with the whole COVID pandemic, we switched over to do all online learning. And this is my life now, of in the morning, coming in front of the camera, doing these live streams, and then in the afternoon, catching up on grading and other paperwork to do. How are things going over in the Ukraine? And I've always wondered, why do we Americans call it the Ukraine? You know, we don't say like the France or, you know, the Spain. Why do we say the Ukraine? Does anyone know? Does it just sound better? I wish we had to answer that. Maybe I'll just Google it. Why do we say the Ukraine? Typed into Google and it actually came up with that as a suggestion. Ukraine is one of the few English country names traditionally used with a definite article, the. This is apparently because the word Ukraina means borderland, and so it would be translated as the borderlands, the Ukraine. Kind of like how Netherlands means the Netherlands, and is translated as the Netherlands.
So, like in Ukrainian, there's a word called krai, which means edge.
Uh-huh.
So, Ukraina means the place of the edge.
Yeah, that's what I was trying to pronounce here off of Wikipedia page, but you pronounced it correctly. What was it? Ukraina? Can you say it again?
Ukraina. That's how you pronounce it.
Ah, and so they translated in Wikipedia as borderland, but you're right, like the edge, right?
Basically, yeah. It's kind of funny, well, in a bad way, because we've always had like people like try and like take over the border. So we've always been a border country. So like there's always been like people invading. So kind of history is repeating itself with our name as well, because people keep trying to take a little chunk of it.
How are things looking over there?
Currently,
Yeah.
they're about the same. There's like, I think the support from the world has really like showed like it's I don't know, its fruits in a way that like we're not losing at all any ground, nothing. And it's only going to get better for us because like the sanctions that were put in place in Russia, like the morale for the war in Russia is like gone because they basically just destroyed their economy like completely. Like they're backed into a corner. And so I don't think it's going to go on for much longer unless Putin decides to pull the nuke card because he's backed into a corner. So,
But that 40-mile convoy of tanks seems a little concerning.
it is a little concerning, but there's also like what's it called? We have drones from Turkey and stuff like that that have like massive amounts of just bombs that can be sent in. That is just like that they can't be shot down or traced because they fly in a way that's like
They're so high, right?
yeah, they're super high up and they're tiny. And by the time it's on you, you can't really stop it. So, and it's really unpredictable because it's like the bomb itself is like a little gliding plane. and it can divert its course either way, and it's super hard to predict. Say compared to like let's say a missile, which is going a lot faster, but it can't like turn away as fast as a well, not as fast as like in a predictable way. It could turn away like a missile can turn away predictably compared to like the plane, which isn't as predictable, so it's harder to shoot down. But I'm not too worried about the convoy. Think that's like what's helping Ukraine at the moment is the fact that they have to go over a mass amount of land to get to any kind of like central city. So that really depletes your troops and really depletes like your resources to get there because you have to spend a ton of fuel. You're moving a tank, which doesn't really go that fast. And it will break down. It's not meant for like longevity over like a duration of a road trip, let's say. But you have to go like through most of the country just to get there. Like compared to like let's say the world wars, Europe is a lot closer together. So like it's easier to send in troops, at least during the second and the first world war. It was easier to send in troops because you're fighting something that's like pretty close to you. You don't have to like travel like a good giant section of land before you get to any kind of warfare or front line.
And plus, it's still really cold over there right now, right?
Oh yeah, Ukraine gets really cold.
So this convoy is having to travel through snow, and it's kind of barren there too, isn't it? Isn't the north and west sides kind of desert-ish?
It's like arid, not arid. It's like just flatlands that are just cold.
Yeah.
There's no cover, no nothing. Just it's like the Midwest.
Yeah.
Yeah. Basically, you're trying to travel through like the Midwest, but like a couple states of the Midwest to get to your battle. So it's not helpful in Russia's cause.
What do you think about that? Those series of text messages. Have you seen that? From
The one that the Ukrainian UN.
Yeah. I mean, there's a lot of stuff going around. Going like, is that real or is that just a?
I have no idea because that's like very like even as a Ukrainian, I'm suspicious of those texts. Like it could be real, it could be fake. Either way, he's trying to humanize the aspect of war. He's trying to like show that hey, these aren't just pawns that you're moving around. These are people that have lives and parents and like they're not just robots that you can just throw into the war. And it's trying to show the fact that like hey, this is a lose-lose scenario for everybody.
Yeah. Well, I hope things get better soon over there, and it is heartening to see how like almost all of Europe and the Western countries have kind of united together to do what they can to help out without getting directly involved.
They don't want to get directly involved, and I completely get why. Because let's say like sanctions, you can't like sanctions do a lot to impact a country. But let's say you were to put soldiers on it, you become the enemy now.
Yeah.
To Putin or to his government, and you don't want to become the enemy and back him into a corner and have him resort to the only option that he has is nukes.
Yeah.
And like, bomb the rest of the world with nukes because that's just game over for everybody. That's not a win.
Yeah. So I can totally understand why people don't want to get directly involved, but there's a lot of indirect stuff they can do.
And the indirect stuff has been massively helping.
They said that ultimately the best thing that anyone could do was just give Putin a way out, right? If he finds himself backed into a corner, give him a way to just sort of like exit gracefully and be done. Abdul says, all our food is from Russia and everything's now gotten really expensive. Has it been 10 minutes already? I've totally lost track of time.
Recording in progress.
Okay, so let's take a little while to walk through this week's assignments. There are 4 files that you need to download to your computer, lessons 5, 6, and 7, plus lab 5. The only one that you're going to turn in is this last one, lab 5, but you need to work through all the lessons. I'm going to walk you through them here so that you can just follow along. I've already uploaded lessons 5, 6, and 7, plus lab 5 to my Jupyter environment. Let's start with lesson 5. So here is the Lucas-Lehmer numbers that were discussed in that video that we watched. You can rewatch the video. Here's a link to the video if you want to watch it again. But this Lucas number sequence is defined like this. So we do a definition by parts. If n is 1, if we're trying to calculate the first Lucas-Lehmer number, the answer is just 4. That's our sort of base number that we start with. And then for any other number, we take the previous number, square it, and then subtract 2. And so for problem number 1, we want to write a function that implements this definition by parts. Let me show you what it looks like. We're going to define Lucas-Lehmer n. So we're going to find the nth Lucas-Lehmer number. And then we just have an if-else here that says if n is equal to 1, then we'll just return 4. Otherwise, else, return Lucas-Lehmer of n minus 1. Right, so find the n minus 1th Lucas-Lehmer number, square that, and subtract 2. And by the way, this square here does not apply to the n minus 1. It will actually apply this whole function first and then square the result afterwards. So run this cell to check your solution. I'm going to hit Shift-Enter here, and I get no errors, so that means my function is working correctly. And then I can also open up a new cell. I can just try it out. Like what's the 9th number in the sequence? You can see it starts to get very big pretty quickly. Here's the 13th number. 15th number. You know, it's now just this enormous number. So you could use this as a starting point to help you determine whether a given Mersenne prime is in fact, or a Mersenne number is in fact a prime or not, by kind of following the steps that they showed you in the video. You don't actually want to deal with these large numbers. You want to do modulo the number you're trying to test as you're going along. So you'll need to redefine this function here so that it does a mod, your target number every time it does a calculation to keep the numbers relatively small. But nevertheless, it can be done, and this could be a quick little primality test for Mersenne numbers. Anyway, we're gonna move on. Problem number 2 is write a function called LL sequence, that takes a number n and returns a list of the first n Lucas-Lehmer numbers. And the hint here is we already have a function that can compute the nth Lucas-Lehmer number. We can use it to build the sequence of Lucas-Lehmer numbers by applying it to the list 1, 2, 3, up to n. Yeah, and Lucas calculated the 126th one. Yeah, that's a crazy thing, right? Huge number. But he was always doing modulo as he was going, right? But still, it's just an enormous number. So use it to build this list here of 1, 2, up to n. So we're going to use map to do this. We're going to map the numbers 1 to n onto the Lucas-Lehmer function that we have, and that will build our list for us. Let's see, did we, oh, we're going to need, since we're using map, we're going to need to use the import, from, I got to make this correct, I got to make this correction on the files that are uploaded to our website so that we make sure we get that map function in there. So we'll map the Lucas-Lehmer function onto a range from 1 to n. And then, oh, we got an error from this. So the way to debug this would be to just go ahead and try it out and see what happens. So if I do LL sequence of 4, I know I should get this set of numbers for 1,494, 37,634. And let's see what I actually get. I only get 3 of the numbers instead of 4 of the numbers. So that suggests to me that my range is incorrect. Remember, the range goes from the lowest number up to, but not including the upper number. So this is going from not 1 to 4, but only 1 to 3. So to adjust for that, I just need to add 1 to my range. And then let's try this out. Oops. And now I get the correct numbers. And so now I'm pretty satisfied that I should run this check cell and it will work correctly. So that's good. Okay, here's the Euclidean algorithm. We went over this on Monday, but here it is in Python. Definition by parts. The greatest common divisor of two numbers a and b can be calculated by just returning a if b is 0. If b is not 0, then we can calculate it by just computing the greatest common divisor of some smaller numbers. And eventually, one of those numbers, the b number, will go to 0, and then the answer will just be a. So here's the Python code to do that. Define the greatest common divisor of a and b. If b is 0, just return a. Otherwise, return the greatest common divisor of b and a mod b. So this is almost a straightforward, actually it is a very straightforward interpretation of the definition by parts. So I'll go ahead and just define that. I hit Shift Enter. And actually, what I wanted to show you was what's going on here when you actually do this greatest common divisor. Let me see if I can show you that. Let's go ahead and define that. GCD of a comma b. If b is equal to 0, return a. Else, return GCD of b comma a mod b. Oh, I need to go back, and below here I'll just say print GCD of, let's pick 90 and 30. We know that that's going to be. Okay, so we're now calculating the greatest common divisor of 90 and 30. So the values of a and b are 90 and 30. I'm going to click on Next, and it's going to go to this next line here. It's going to check to see if b is equal to 0. And it's not. B is equal to 30. So we know that when I click on Next, it's actually going to jump forward to line 4 or line 5. And it does. It goes forward to line 5. And so now it says return GCD of B and A mod B, which means when I click on next, what's going to happen is I'm going to get a new frame down here, so a second call of GCD with A is 30 and B is 0. Okay, so literally GCD gets called twice in this case. The first time with the original numbers, and then the second time with these smaller numbers. So within this second invocation of GCD, it's going to check to see if B is 0, and it is. So now my arrow jumps forward to line 3. It's going to say return A, the value of A. So the value of A is going to come back up to this first invocation. So here's my return value of 30. Okay, and then this first invocation takes that 30 that came back from the second one, and that becomes its return value. And that gets passed back up to the print statement, which prints out the number 30. Let's try that again, but let's do 26 and 7. Okay, so we start out with GCD with 26 and 7. B is not 0, so it's going to jump ahead to step 5. Okay, so now A is 7 and B is 5. Now in this case, B is not 0, so it's going to jump ahead to step 5 again, and we'll get a third call to GCD. So you can see the numbers for A and B are getting smaller and smaller and smaller. Okay, B is not 0, so we'll get another call. So now we got 4 of them stacked up. B is not 0, so we've got another call to GCD. Now we've got 5 of them going. But so when I say 5 of them going, it doesn't mean that 5 of them are going simultaneously. The only one that's really going is just the very latest one. Now we've got B is 0. So we're just going to return A. The return value is going to be 1. And so that return value is going to go up to the fourth one, and its return value will be 1. And then that one will go up to the third one. Its return value will be 1. And so this 1 is being passed back up the chain to finally being the value that gets printed out up here. So when you write a recursive function, it literally, inside the computer, starts stacking up these frames, each one of them having its own local copies of the variables. And then once the lowest numbered or the most latest frame returns, then this stack starts to unwind itself and go back up to the original one. There's a question here in the chat about, does Python do tail call optimization? And it doesn't. Python explicitly does not do tail call optimization, which is a way to turn a recursive function into basically a loop. And so some compilers and some languages will recognize when this happens and turn it into a loop, but Python is not one of those. Okay, so we're back to our lesson here, and hopefully you got a little bit of a visualization about what's going on there in a recursive function. Okay, problem number 3 is implement the least common multiple function. It takes two numbers, A and B, and returns a single number that's the least common multiple, and here's the formula for computing this. So this is easy to do. You just say return absolute value of A times B. And now we want to use divide here, but we're dealing only with integers. We're never going to deal with fractions or decimal numbers, so you might as well use the integer division in order to do this calculation. GCD of A comma B. And then we'll check our solutions. Good. Okay, problem number 4. We can use the GCD function to determine whether two numbers are coprime. Numbers are coprime if their greatest common divisor is 1. So we can write a function called is coprime that determines if two numbers A and B are coprime, return true if their GCD is 1, and return false otherwise. So if GCD of A and B is equal to 1, return true. Else, return false. Don't forget to put your colons after your conditions, and the notebook will automatically indent the bodies of your conditions and functions for you. And we'll check it out here. And everything passed, so we're good there. Any questions about that so far? By the way, I wanted to show you something. Let me go up to the definition for GCD here, and there's actually a more compact way to write these if-else statements if the thing that you're doing is really simple. Like if you're just evaluating a simple condition, and the thing that you're returning inside of the bodies of the conditions consist only of returns and just calculations. So if it's really, really simple, you can actually do a much more compact version of this. Let me go define GCD, I'll call this 2, version number 2. And we'll just say return, we'll just go right into a return, and we say we'll return A if B is equal to 0, else GCD of B comma A mod B. All right, so instead of going if B equals 0, return A, else return GCD of B A mod B, we'll flip this all around and just say return A if B equals 0, otherwise this thing. So either return A or this thing if B is 0. And let's try it out. GCD 2 of 1526, that's 1. And we'll do 13 and 26, and that's 13. So this is like a more compact way of writing an if-else, if the thing you're doing is really simple. We can go down here to, let's do is coprime, and let's write it a different way. We'll say return true if GCD of A and B is equal to 1, else false. Okay, and these all pass the test. And in fact, if all you're doing is either returning true or false, then that means that you're essentially returning the very value that you're calculating. So if GCD is equal to 1, if that's true, you're going to return true. And if that's false, you're going to return false. So if you're already calculating whether the GCD is equal to 1 or not, you can just return that. So in this particular case, since we're just returning true or false, we could just say return GCD of A comma B is equal to 1. So if this is true, that's the value we'll return. And if this is false, that's the value we'll return. Thank you, Akash. So this is exactly the ternary operator like in C, but it's much easier to read because it uses the words if and else rather than question marks and colons. And also you reminded me about just returning whether the GCD is equal to 1 or not without doing an if-else at all. So this is a good start for GCD. We'll come back to this function in a little bit. Okay, lesson number 6. We already know about a function called map that's used to apply a function to some kind of iterable collection, like a list or a set or a string. But now we're going to learn about a new function called filter. It still kind of works in the same way that you're applying a function to a list of things, but instead of transforming each element of that list into something else, what filter does is it decides whether or not to keep elements of that list. So you can apply a criteria to each one of the elements and discard the ones that don't meet the criteria. Just like with map, there's a built-in filter function, but it doesn't return results necessarily that are easy to interpret. So I've written a filter version, a version of filter that works a little bit better for beginners. So again, you'll need to import the Computer Science 26 library. And then here's a function that just determines whether or not a number n is a multiple of 7 or not. And here I've written it out in kind of like the long format where we check to see if it's equal to 0, the mod 7 is equal to 0, and then we either return true or false. We could, of course, shorten this quite a bit by using those techniques that I just showed you a few minutes ago. But let's go ahead and define this function, and then we'll use filter to apply this function to the list of numbers from 0 to 99. So I've got my range here. This is going to build a list of all the numbers from 0 to 99, and then we're going to apply this is multiple of 7 function to each one of those elements and discard the ones for which that's not true. And we end up with just the numbers 0, 7, 14, 21, 28, all the multiples of 7. Okay, so the function that you use for filter needs to be a function that either returns a true or a false. Okay, the map function could be a function that takes a number in or a value in and transforms it into something else. But the filter function needs to be a function that takes a value in and either returns true or false. So here I've shown you that you could rewrite is multiple of 7 using this shorter format, and it still works. So we still get the same list. Okay, and here's one that defines a function called is odd, and it returns a true if the number is odd and a false if it's even. So we're going to apply this function is odd to the range of numbers from 1 to 19, and then show us the values. So the value of odds is the numbers 1 through 19. So I kind of like this because rather than try to develop a function that directly calculates odd numbers, you could start with a list of numbers that's easy to calculate, just like using the range function, and then use filter to winnow that list down to just the values you need. So start with a list that's bigger than you need, and then use filter to discard the ones that you don't need. So I kind of like to think about, and this is actually a lot of the ways that I write my own programs kind of in my personal life is I start with a collection of data, and then I start to write filters for it that successively reduces the size of that data so I get just the stuff that I'm looking for. And I might do it piece by piece. One of the things that things like system administrators do is they might have a process running on one of their servers that generates a lot of data, a lot of diagnostic data. Things like web servers. Every time someone goes and requests a file off of the web server, whether that file be an image or an HTML file or a style sheet file, every single one of those requests gets logged in a file to indicate who requested it, when did it happen, what file did they request, how big was it. There's all sorts of data there. And maybe as a system administrator, as a network analyst, you might want to know things like what's the most common file that people request, or when do most requests come in? Like, when's the busy time of the day? Is it in the morning? Is it in the evening? Is it at night? And so you could take this giant log file that contains too much information and then start applying filters to it. You know, every line in the log file contains who requested it, what IP address did they come from, when was it requested, what file was requested, how big was it, what page were they on when they requested that file. So there's a lot of information in there. But we're only interested in, let's say, just the file name. So we could take this huge amount of data and apply a filter that selectively discards the stuff that's not file names, discards the dates, discards the IP addresses, discards status codes and things like that, and leaves behind just the file name. And maybe you don't get just the file name, maybe you get a path name, right, containing all the subdirectories. So then you apply another filter that goes through those and pulls out just the file name. You know, or maybe you're only interested in what files were they requesting between the times of, let's say, midnight to 6 a.m. So you might write a filter that first goes through and discards all the lines that don't have anything to do with anything before midnight or after 6 a.m. And then you go through and filter the lines for just the piece of information you're looking for. So successive filters to winnow down the data and look for just the pieces you want. Yeah, for a system administrator would use something like grep or awk or sed or perl or, you know, one of the tools that are out there they're really designed for doing just this. Okay, so we can use filter to reduce the size of a list. We can use map to transform a list from one set of values into another set of values. So here's one that will transform the list of numbers from, this one here will take the existing odds list, which we calculated up here, and square all the values. So we can combine map and filter together to do what we want to do. And so let me take a moment here and again give you a little tidbit of stuff that you could use in your programs. This is not in the lesson here, but I'm going to show it to you if you're watching. Let's see if we can combine the map and the filter together in one line to do this rather than doing it as separate statements. So let's open up a new cell. So I started out with the range of numbers from 1 to, what was it, 20. And then I just wanted to filter those out so it's just the odd numbers. So let's go filter. I'm going to put that in front, is odd. Okay, and that gives me the list of odd numbers. And then from that, I could map square onto that. And that gives me the same list of numbers. So I started with the range of numbers from 1 to 20, and then I used filter for is odd, and then that gave me a list of just the odd numbers, and then that was passed into map, and I applied square to it. Okay, so I'm able to do now in one line what previously took me 3 or 4 lines to do. And then I can go one step further. Not only did I have to do 3 or 4 lines to compute this, I also needed those 2 functions, is odd and square. I needed to define those functions. Here's the one up here, and here's the one up here. And using lambdas that we learned about last time, and we'll get to again in just a moment here, using lambdas, I can actually dispense with those auxiliary functions entirely. I can replace this is odd function here with a lambda that does the same thing. So instead of putting is odd here, I put in a little anonymous function that takes in a parameter called x and then and then returns true if x mod 2 is 1, and returns false if it's not. Let's see if that still produces the same result, and it does. And then the same thing for square. I can pull that out, and I can replace it with a lambda. Let's do n here, n squared, and we still get the same result. So lambdas, in case you were wondering, what good were lambdas? Lambdas are great for things like map and filter, because you can just do quick little nameless functions right there in that first parameter to winnow down the list or transform the list without having to write a whole separate function just for it. Now, to be honest, this gets a little hard to read because there's a lot of stuff going on in one line. But if you just really quickly want to write a little nameless function, you just want to basically apply an expression to each element of a list, lambdas are great for that. Okay, well, we'll go on and we'll see that again in just a few minutes. So problem number 2, use filter to construct a list of the primes between 2 and 47 whose last digit is 3. Assign this list of the primes to variable. I gave you a list of the prime numbers between 2 and 47, so you don't have to write a function that generates the list of primes. So you're going to write your solution here. So we'll need a function. Oh, we don't have to do that. We can just go prime3 equals filter. Now, so we want to know if the last digit of a number is 3. So we can do that by doing a mod 10 and look at the remainder. So if we divide the number by 10 and look at the remainder, that'll essentially isolate just the last digit of that number. Oh, not is last 3, last is 3. There we go. Good. And then we'll run that cell, and then we do get the correct answer there. Now let's see if we can do that with a lambda. So rather than defining this whole function here, I'm basically going to take the body of this function and plop it right in to where the name of the function was. So we'll go lambda. Let's do n mod 10 is equal to 3. And then run this again, and we still don't get any errors, so that worked. You can do the same thing in Java. Java introduced lambdas in like version 8, I think. 8 or 10, somewhere in there. And so now you can do lambda functions in Java, which you couldn't do up prior to that, which means up to about 3 or 4 years ago, you just couldn't do lambdas. And a lot of Java programmers thought, well, what's the use of them? But now that they have them around, very many of the library functions that deal with things like key presses and mouse clicks suddenly become a whole lot easier because you no longer have to define a whole class and a whole method just to deal with that mouse click. You can now just put a quick little lambda expression right into your mouse click handler. You know, like let's say if every time you click the mouse, it just bumps your score up by 1. Something like that, right? You click, 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 cookie clicker, right? You click, 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 and every time you click the mouse, it bumps your score up by 1. You can do that with a really quick little lambda expression that just takes care of that, rather than having to make a whole class and a whole method just for it. Really cool. Problem number 3. Assign to the short states variable the list of the states whose name is 6 or fewer letters. You can use the states list as a starting point. There we go. And you can use the built-in len or length function to determine the length of a string. So I'll let you figure that one out. Okay, but it'll be similar to the way this one was done over here. All right. tuples, or also pronounced tuples. I go with tuple myself. It's kind of like a fixed size array, except that you can't add anything to a tuple. You can't change a tuple once you define it. Tuples, you've seen them used in your math classes for things like XY coordinates on the Cartesian plane. Or it could also be used to store information, let's say about a car. You've got the make, model, and year. So 3 pieces of data about a car. Or maybe someone's name. You got their first name and last name. Or given name and surname, depending on what you call it, right? So it's a pair of values, or 3 values, or 4 values. And so in Python, you put them in parentheses. So arrays or lists are done in square brackets. Sets are done using the curly braces. And tuples are done using the parentheses. So here's a tuple that defines the pair 3 and 4. Here's one that's Toyota Camry 2015, and here's one that's James Bond. Okay, simple little tuples. But what tuples could really be used for, a really cool place to use them, is for returning multiple values from functions. See, in a traditional language like C or Java, you can only return one thing from a function. And in Python, that's still the same, right? You can still only return one thing, but that one thing could be a tuple, which could hold multiple values in it. So here's the quadratic formula. Remember this from your math class. It allows you to solve a quadratic equation, but it usually has 2 solutions to it. There's usually like a positive and a negative solution. This plus or minus here gives you the 2 solutions. So this returns 2 values for x that both satisfy the equation. So here's a function where you plug in the 3 coefficients, a, b, and c, and then it computes the plus solution and the minus solution. You can see the only difference between them is the plus or minus right here. And then returns the pair of numbers. So we stick them into a tuple using the parentheses, and then it will return that thing back to the caller. So in Python, you can return multiple values by just stuffing them into a tuple. So here's the solution to 5x squared plus 6x plus 1 equals 0. And here's the solution to x squared plus 4x plus 5 equals 0. And notice here, we actually get complex numbers back. And in Python, complex numbers use the letter J instead of the letter I. And that's actually because the developer of Python, or the developers of Python, were engineers. And in engineering, J is typically used instead of I, because I is a symbol that's used to represent electric current. And so J is typically used to mean the square root of -1. And so that carries over into Python, where J is now used to represent the imaginary numbers. So just imagine that there's an I here instead of a J. But we get -2 plus I and -2 minus I as our 2 solutions. Okay, so since a tuple is just another data type in Python, you can assign it to variables. So here I've assigned the variable GPS to these 2 coordinates. And you can access the individual coordinates of a tuple just like it was an array. So you use the square bracket notation, and you can access element 0, element 1, element 2, and so forth. Okay, but here's the really nifty thing you can do with tuples. You can use it to assign to multiple variables at once. So here I've got a tuple consisting of the variables lat and lon, and I got another tuple consisting of those 2 numbers. And what's going to happen here is it's going to take 38.79 and put it into the first variable, and take a negative 121.21 and put it in the second variable. So you can assign to 2 or 3 or 4 variables all at once using tuples. And this is a really cool thing you can do in Python. So I can take the output from the quadratic function and assign them to x1 and x2 simultaneously. And I can see what the answers are individually, or I can pack them into their tuple again. Right? So returning values from a tuple, returning tuples from a function is really cool because you can then use that tuple and assign them individually to separate variables. So problem number 4 says, assign the variables department, number, and name to the values computer science, 26, and discrete structures all at once using a tuple. And it's going to look like this. Department, number, and name equals CSCI, 26, discrete structures. Okay, so computer science goes into the department, 26 goes into number, and discrete structures goes into name. So cool to be able to do that. So the last problem on this page is write a function called QR that takes as input a numerator and a denominator, n and d, and it returns a pair of numbers. The first number is the quotient, and the second number is the remainder. So if I plug in 8 and 1, I should get 8 and 0. If I plug in 7 and 2, I should get 3 and 1. I really highly suggest when you're writing these functions, go ahead and look at the checks, the assertions that are done below. If they're written in a very straightforward manner, like I've got here, you can use that to help you write your function, because now you can see, oh, the function QR is going to return a tuple. So I need to make sure that I return and then two things inside parentheses. Like up, where are we going? Up, up, up. Up here. No, not this one. What am I looking for? Oh, like here. My assertion for short states returns a list. So I need to make sure that when I write this function, or when I write this expression, that it results in a list. Where's another one? These are all lists up here. All right. When we get to the actual assignment itself, look at the assertions and see what kind of thing it's supposed to be, and make sure your function returns that type of thing. So after the return statement, you ought to see, like if it's supposed to return a byte string, make sure there's a byte string there that it returns. I mean, let's zip all the way down to the bottom again. We were, I think, pretty much done with this. So I'll leave problem 5 up to you. Write a function that takes in two numbers, n and d, and returns a pair of numbers. The first number is the quotient, integer quotient, and the second number is the integer remainder. I think you can handle that. Let's pop over to lesson number 7. Sorry, I'm kind of hurrying through this because there's 4 files to get through, and I've only got, 20 minutes left. So we'll get through it here. So again, here is a review of lambda functions, and this is what I wrote last night at midnight, so I hope it's coherent here. We introduced lambda functions last time, but let's practice them. So remember what they look like. It's the word lambda, and then the list of parameters that it takes, and a colon, and then an expression that computes something with those parameters. So lambdas have no name, so you don't give these functions a name. They're very compact. They consist only of inputs, a body, and a return value. There's no name associated with it. And also, lambda function bodies are limited to just a single expression. This is a little bit different than other languages. I think in Java, Scheme, ML, Haskell, lambda functions can actually have giant bodies, but in Python, they're just very, very short. The intention there is that they get used for just very short, simple things. Anything more complicated, go write a regular function for that. Okay, so here's a lambda function that simply determines if a number is odd. And if I was to execute this, I get this weird cryptic output here, but here's how you decode that. First of all, it says, I've returned to you a function. Don't worry about this main thing here. I've returned to you a function. It's a lambda, and it takes a single parameter x. If I execute this one here, it says, I've returned a function to you, I meaning the computer, I've returned a function to you, it's a lambda, and it takes a single variable n as its input. So lambdas are useful as function factories. You can write a function that returns a lambda. So the outer function is essentially constructing an inner function based upon its inputs and returning that to the caller. So it's generating functions. It's a function generator, a function factory. So here is a function that determines if a number n is between 20 and 50. This is just an ordinary function here. Is between 20 and 50. So return whether n is greater than or equal to 20 and less than or equal to 50. And so we can very quickly determine if a number is between 20 and 50. So is 45 between 20 and 50? Yeah. Is 99 between 20 and 50? No. And then here's one that determines the numbers between 90 and 100. It looks almost exactly the same as the 20 and 50 function, except that the numbers are different. So instead of 20 and 50, it uses 90 and 100. So is 99 between 90 and 100? Yes, it is. So if you look at those two functions, let's see if I can get them both on the screen, you can see that the bodies of them are very similar, in fact, almost identical, except that these numbers, the minimum and maximum numbers, are different. So whenever I, as a programmer, see that sort of thing, that I've got two or more statements that are very similar, except that a couple things are changing, or two or more functions that are very similar, except only a couple things are changing, then what I want to do is generalize that into one function that just takes parameters for the things that are changing. So here, I've made a function called isBetween that just accepts as parameters those minimum maximum numbers. And what it generates as a factory is to produce a function that accepts one parameter, the number that we're testing, and determines if that number is between the minimum and maximum. So I'm just taking the minimum and maximum here and turning them into variables. And so what isBetween does is it creates it defines a function whose job is to generate new functions. So what's the difference between a function that returns a function and a function that just simply takes all the parameters? Like, couldn't I just make a function called isBetween that takes a minimum, maximum, and an n? And certainly you could, if that's your ultimate goal, is just simply to test whether n is between the minimum and maximum. But what we're using this for is to be able to turn a function that normally would take, let's say, 3 parameters into one that only takes 1 parameter, with the other 2 being fixed values. Because we'll be able to plug those kinds of functions into map and filter. Map and filter, the functions used for map and filter must be a function that takes 1 parameter and only 1 parameter. And for map, it returns a parameter, it returns a value, and for filter, it returns true or false. So map and filter need to have functions that take only 1 parameter. And so what we're using the lambdas for here is to essentially transform a function that would take 2 or 3 or 4 parameters into one that only takes 1 parameter and then sets the other ones to be fixed values. Okay, so I've got this function called isBetween. You pass in the minimum and maximum values, and then it gives you back a function. A function that's a lambda, and it takes a single parameter n. Okay, but by itself, it's not that useful. But we could give it a name. So we can bind this to a name. In this case, I've called it is teenage. And then I can use it like a regular function. So I've used the in-between function to create another function that tests to see whether its single parameter is between 13 and 19. And if it is, we say that if we plug an age into that, we say, okay, that person is a teenager, which I guess is an American term because we use numbers that end in the words teen to indicate that they're a teenager. Okay, again, here's a kind of an American thing here. Create a function called isBoomer that determines if a person is a baby boomer, which is somebody who was born between the years of 1946 and 1964. And I'm not going by the current millennial definition of boomer, which is basically anyone over the age of 30. Oh. Let's see, you're asking the question, can I do this? Can I go is between 13, 19, and then 15? So is this going to work? And the answer is yes. Right? So what did this do here? So is between generated a function. So the result of this first part here that I'm highlighting in with the red circle is itself a function. And then right over here is the invocation of that function and passing it the number 15. So yes, this will work exactly like you thought it was going to work. Okay, problem number 1. Create a function called isBoomer that determines if a person is a baby boomer. That is, they were born between 1946 and 1964. Use the in-between function factory to do this. So I think you can handle that. It's going to look a lot like this one. Oh, sorry, it's going to look a lot like the teenage one here. Okay, problem number 2. We're going to see the use of these lambdas in a different context. Oh yes, JavaScript is full of lambdas, full of it. I think, if I can digress for a moment, I think it's kind of one of the reasons why I think JavaScript does not make a suitable language for beginners to learn, because the beginner invariably starts going off and Googling, like, how do I do this? How do I do that? And then the solutions they stumble across are full of these weird things that are actually lambdas. And then they like, oh, what the heck is this? I'll just copy and paste it and hope it works. And it's not necessarily because the lambdas are there. It's because some JavaScript libraries, some frameworks are written in a way that makes extensive use of the lambdas, and some of them are written so they don't need them. And I think for the beginner, you get this mix of stuff with this syntax you've never seen, and it's just confusing. And so you kind of have to learn those things up front, but it's really hard for a beginner to learn those things because you're struggling with just basic stuff like loops and conditionals. And here's this, it's not even called a lambda, it's called just a nameless function, right? It goes function, parentheses, parentheses, and then a little arrow, and then a big body, right? And then you get weird stuff like at the end of all this is like curly brace, parentheses, semicolon, curly brace, right? All these closing brackets at the end. And it's just a big mess. If you're an experienced programmer, it makes sense. You're able to format the code so it looks nice. But for a beginner, it's just a horrible spaghetti mess of junk. Lambdas are definitely usually used for things like callback functions. Anyway, so we've got 10 minutes left here. So here we go. Problem number 2. A few weeks ago, you learned about the Boolean logic operations and, or, not, exclusive or, and so forth. Those operate on Boolean values, either true or false, or 1 and 0. But there are also these things called the bitwise operators. They also have names like and, or, and not, but they work on numbers rather than Boolean values. So the way that work on numbers is if I, let's say, do the exclusive OR operation, what I do is I convert the numbers into binary. So here they are converted into binary. And then I just operate on them column-wise. So I'm applying the exclusive OR operation on each column of bits. So 1 exclusive OR 0 is 1. 1 exclusive OR 1 is 0. Same thing here. 0, 1 is a 1. 1, 0 is a 1. And so forth, just down the line, either from left to right or right to left. So columns of bits get the operation applied to them, and the result is a number. So in Python and in C and in Java, the bitwise exclusive OR operator is the caret, the upside down V. It's on my keyboard, it's a shift 6. So if we do 87 exclusive OR 142, you get 217. And if you want to see the binary value of 217, you can use the bin function, and we can just compare. Is the answer I got here the same as what's in the table? And you'll see that it is. And so the reason why I brought up this exclusive OR is because this is actually another way to encrypt data. You can use the exclusive OR operation. You come up with a secret key, which is a number, and then you just apply exclusive OR to every letter in your message, and that's one way to encrypt. So we got a function here called exclusive OR 37 that applies exclusive OR 37 to its input x. The other one's called exclusive OR 255 that applies 255 to its input. So let's define these. So we'll say return x exclusive OR 37, and this one down here is return x exclusive OR 255. All right, those are easy, and then we'll do all these checks, and yeah, they all work out. So you can see, again, I've got an example here where the only thing that's changing is this number. The bodies of the functions are identical, except this number is changing. So we're going to turn that into a variable. We'll call it B. B, I guess, stands for byte, right? We'll return lambda x, and we'll go B exclusive OR x. Or we'll do x exclusive OR B. It doesn't matter which order they go in. Yeah, you're right. Right, Akash. The nice thing about encrypting and decrypting with exclusive OR is you just apply the same operation twice. You do exclusive OR to encrypt, and then you just do the same exclusive OR again to decrypt. So that's one of the nice things about using exclusive OR. Okay, so we will check this, and did this work? Did this not work? Actually, it looks like, oh, invalid syntax. I have a typo. This is what happens when you write these things at midnight after a long day. I have a typo, so I have to go fix that. Okay, so, oh gosh, 5 more minutes here. So generating coprimes using GCD. So we turn now back to the greatest common divisor function, which we were talking about half an hour ago. So here it is from from lesson 5. And if you want, you can turn it into the ternary operator version. Let's go ahead and do that. I kind of like that one. So we can go return A if B is equal to 0, else GCD of B A mod B. Oh, nice and compact. Okay, so you can use that GCD function to determine if two numbers are coprime. If the greatest common divisor is 1, then you know those two numbers are coprime, right? So here, I've got a function that is going to determine whether a number is coprime with 15. So if the greatest common divisor of that number and 15 is 1, then we know that number is coprime with 15. And then we can use that function in combination with filter to come up with the list of all the numbers that are coprime with 15. Okay? So we got a function that determines if a number is coprime with 15, and then we can use that with filter to start with a list of all the numbers between 1 and 15, and then discard the ones that aren't coprime. Here's another example of that. Is coprime with 36. It determines whether a number is coprime with 36, and then we combine that with filter to come up with all the numbers that are coprime with 36. Hopefully you can see where I'm going with this. All right? The bodies of these two functions, almost identical, except these numbers are changing. So of course, we'll want to generalize that into a function called is coprime with. You pass in the number that you want to see if it's coprime with, and all we have to do here is replace the word none with an expression. Right? So basically, you look at how this expression is constructed, and then just, swap it in, except with the thing that's changing as a variable. Okay, and then we can use that function to now generate all these new functions to see whether numbers are coprime with some other number. And then we can use that in conjunction with filter to produce lists of, this is basically now the totient function. Right? Remember, the totient was the number of numbers that are coprime with a given number. So we'll start by generating all the numbers that are coprime with it, and then just find out how many of them there are. So I write a function called coprimes of that takes an integer n and returns a list of integers in the range 1 to n that are coprime with n. Okay. Coprimes of n. Okay, so we'll just say return. And you see how we came up with a list of all the numbers that are coprime? We used filter. Filter. Okay. But then after filter, if I can scroll up here again, after filter was is coprime with, and then the number that we're interested in finding out, the numbers that are coprime with. So we have this new function called is coprime with, where was it? Here, up here. And then we just pass in the number n, and it'll generate a function for us that will determine whether a number is coprime with n, and then we'll just pass in the range from 1 to n. And no errors there. Okay, let's open up a cell. I want to see how this thing works. Coprimes of, and you just pass in a number, like 45. And it comes up with a list of all the numbers that are coprime with 45. Or coprimes of 80. And here's all the numbers that are coprime with 80. Or coprimes with 99. Here are all the numbers that are coprime with 99. There's a lot of them. So finally, last problem on this here. Write a function called totient. It takes a number n and tells you the number of numbers that are coprime with that. All right, so this should be easy. We have a way to generate a list of all the numbers that are coprime with n. All we have to do is figure out how many of them there are. And there is a function called leng, L-E-N, length, that will return the length of a list. So this is easy, right? Define the totient of n. And we just say return the length of whatever this thing returned up here. Scroll up. Whatever this thing returned. So we'll generate a list of all the coprime numbers less than n and just figure out how long it is. And very straightforward way to do that. So in this case, we could have done something like plug it into those properties, but that involves knowing whether it's prime or not and how to factor it into primes. So that, might be a more straightforward way to do it, but straightforward in terms of it comes up with the answer efficiently. But here's just a kind of a quick and dirty way to do it. Just generate a list of all the numbers that are coprime with n and just figure out how many there are. Phew. Okay, so we're going to go over time a little bit, but I got to quickly cover Lab 5, and this is the one that you actually turn in. So here is the extended Euclidean algorithm. Remember, this was a way to compute the multiplicative inverse, except that we don't have to do a guess and check. We don't have to just try combinations of x and y until we stumble across the answer. I'm going to call this EGCD, extended GCD. You plug in a and b, it gives you an x and a y. So if b is 0, just return 1, 0. This returns a pair of numbers, remember? So we're going to return a tuple. Here's where the tuples come in. EGCD returns 2 numbers, x and y. So we're going to return 1 and 0 if b is 0. And then we're going to return t comma s minus q times t when b is not 0. And here's the definition of what q, s, and t are. Q is just the quotient of a divided by b. And s and t you get by recursively calling EGCD with b and a mod b. You should recognize this, b a mod b. It looks like the call to GCD, except this is EGCD. So we can turn this into a Python function. I've given you some hints in the comments below here. So the first thing to do is calculate q, the quotient, using integer division. That's this right here. Oops, trying to highlight it. That's this right here. So calculate q, the quotient of dividing a and b. Use integer division so you get an integer quotient. Then calculate s and t by calling EGCD of b a mod b. So you can almost literally copy and paste this into the code, except you have to change the mod into a % sign. And then finally return the tuple t comma s minus q times t. You can do that. Pretty sure you can do that, right? And then run this cell to check your function. Okay, multiplicative inverse. Quick review here about why we want to do multiplicative inverse. But remember that the multiplicative inverse can be calculated by using the extended Euclidean algorithm and just plucking out the first number you get back. You're going to get back 2 numbers. You only need the first one. So you're going to write a function called multinv that takes 2 numbers, a and n, and it should return the multiplicative inverse of a mod n. Okay, so you can do that by calling EGCD of a and n and get back a pair of numbers, x and y. And then just return the first element, return the x value. Sometimes you get back a negative number. Sometimes for x you get back a negative number. What we really want is the positive number. That's easy to handle. You just do one last mod of n and you'll get back the positive number. Okay, the details about that are in this paragraph up here. So you're going to get back an x value. It might be negative. If it is negative, just go ahead and do a final mod n and you'll get the positive number. If the answer is positive, just go ahead and do a final mod n and you'll get back a positive number. So you don't have to do a condition there at all. Just return x mod n and you'll get back the positive number. Okay, so finally, decrypting the linear cipher. So this first function called decrypt, it decrypts a single character, not a whole string, just a single character. you give it the ciphertext character value, a number, not a character, a number, and the M and the K, and it returns to you the decrypted value. So you're going to calculate that by subtracting K and then multiplying by its multiplicative inverse. So you're going to have to throw that into the multiplicative inverse function that you just wrote, get back a value, and that's what you're going to multiply by. Okay, so you're going to take C, subtract K, and then multiply by the multiplicative inverse of M mod N. And you have a function for finding out the multiplicative inverse of M mod N. You just wrote it right above. And then finally, problem number 3, you're going to do linear decipher that takes a multiplier M, the offset K, and the ciphertext, a string, and it's going to return the decrypted string. Okay, you're going to do that by applying your decrypt function that you just wrote here to each letter of the string, each character of the string. And you're going to need a helper function for this. You might want to look at the previous assignment where you did the linear cipher and see what that helper function looked like, and use that to model, use that as a model for what the linear decipher function should look like. So the linear decipher partial is going to be a lambda. It's going to return a lambda, but it's going to be using this formula instead of the encryption formula. And then the linear decipher is going to be using a map to map that linear decipher partial function onto each letter of the string. And then try it out. So here's some stuff that'll decrypt correctly, and then you can try it out yourself. If you are able to successfully decrypt this code, you should get something that you can read in English. Okay, whew, boy, that was a lot of stuff, right? This is, you know, I'd say this is probably so far the most complex assignment you've done, because it's now putting together all this stuff that you've learned. You've learned about lambdas, making functions, map, and filter, and tuples, right? A lot of new stuff. And not all these things are unique to Python. As I said earlier, Java is starting to roll some of these features into its own language. And it's really kind of because of the influence of languages like Python and Haskell and Scheme that have been able to do this for decades. The people that develop Java are feeling kind of the pressure. Like, if we want to make Java still be relevant in the year 2022, we have to keep rolling in these new features that other languages have, that other programmers like to use, but Java doesn't have. So we got to figure out how to roll those things in. And that's what they've been doing over the past few years. So I really like some of the changes they've done to Java. Not all of their implementations are as clean as they could be, because Java is a compiled language, and a lot of these features like lambdas really work best in interpreted languages where you can kind of change things on the fly. But the Java people have figured out how to do it. It's kind of cool. They've all made it backwards compatible with Java 4. So even if you write a program that uses lambdas, the bytecode it produces will still run on old Java virtual machines from decades ago. Okay, wow, that was a lot of stuff. So if you didn't get it all watching me live, then of course once the recording is posted, you'll be able to go back and pause the recording and fill in the gaps. And do send in your messages, your emails. I got one late last night at 11 o'clock from a student who was a little confused about the lambda stuff, and so I was able to help them out. But it also informed me that I need to do more stuff with the lambda, so that's why I wrote this whole lambda section around midnight after answering that email, going, oh, I need to have more practice on that. So boom, out came that practice section for lambdas. I may eventually incorporate that more into Lab 4 sort of up front, but here it is in Lab 5. Okay, I feel like I just talked for 3 hours. So where are we going from here? Next week, we're going to start talking about public key crypto systems, RSA in particular, because it's one that is used by modern browsers, anytime two people need to send a message to each other and do it in a secure fashion, RSA is probably getting used behind the scenes to encrypt and decrypt your messages, whether it's web browsers or your direct message, instant messaging applications like WhatsApp and iMessage and a lot of the others. Everything is now these days just encrypted by default. And so things like RSA get used. So we'll talk about the calculations that are involved there. And yes, the stuff like EGCD and Totient and multiplicative inverse and are all going to come back and get used again in that as well. So it's kind of nice that a lot of these topics that we've talked about as far as linear cipher are really used for modern, secure, ultra-secure cryptography in the form of RSA, and I think also for ECC, those get used as well. So we'll come back on Monday and Wednesday and talk about RSA, and then the week following that, so either 2 weeks from now or possibly a little bit later than that because of spring break. I'm not sure where spring break falls exactly this year. But after we talk about RSA, then we'll talk about hashing, which is not an encryption method, but it's a way of obscuring things like passwords, so that if somebody stumbles across a list of hashed passwords, they can't very easily just reverse it back to the original password. They can't just decode them and figure out what the original password was. And so I will show you, along with how hashes work, is how do actual professional password hackers actually decode passwords? What do they have? They have to basically resort to brute force. But what tools do they use? How do those tools work? And I'll give you a demonstration of those. So by the time you leave this class, you'll know how to encrypt and decrypt messages using modern cryptography methods, and you'll know how to crack passwords. So you're well on your way to being a cyber criminal in this. No, I mean, I think by showing you this stuff, I am lifting the hood on what is sometimes a totally mysterious process. And by doing so, I'm giving you the tools to understand that really this stuff is not very hard. And maybe you'll find yourself in a position where you want to start a career in cybersecurity or network security, and you'll have some of the tools under your belt. You'll kind of know what your adversaries are doing so that you can combat them more effectively. Okay, so that's it for today. We've gone way over time, but I hope you enjoyed the topics from today. I saw what started out at the beginning of the semester with just 1 or 2 viewers. For this, the C class was always very popular, but this discrete structure class started out being like 1 or 2 people, and now it's ballooned into 6, 8, 10 people watching. So that's very cool. Why not just encrypt passwords? Because if somebody stumbles across the secret key, they can decrypt all the passwords. So you don't want to encrypt passwords. There's a great video on YouTube about why you don't encrypt passwords. Let me see if I can find that. I think it's called How Not to, yeah, here it is. How Not to Store Passwords. And it's this one here by Computer File. Okay. Well, I hope you all have a great weekend if I don't see you on Thursday. If you do come back on Thursday, what are we doing on Thursday? I think we're learning about version control systems. Git in particular. I think that's what we're doing. So come back if you're interested in learning about that in the C class at 9:30 on Thursdays. Otherwise, I will see you next week. have a great rest of the week, and I'll see you later. Bye-bye. Yeah, so the whole purpose of this class is to show you some of the math that underlies these very practical topics in computer science, like encryption and decryption. Later on, it'll be compilers, programming languages. Some people have said all computer science, all computer programming is just math. And really, to some extent, that's true. You know, it's all just numbers inside the computer. But one of the purposes of having all these frameworks and libraries is so you don't have to deal with the math. But I think as a computer science student, it's useful to know some of the things that are going on underneath there, just so you can get this idea that it's not really all that mysterious. It's not really all that hard. And be willing to open the lid on other things you stumble across and see how it works. Okay, well, I'm glad you all could join on this stream, and we'll be back, like I said, next week to start talking about RSA. And that'll be fun, because by the end of the week, you'll be able to encrypt and decrypt messages in Python and send them to someone else, and then they can decrypt it and turn it back into the original text. I still need to, in my copious free time, figure out how to get some of this material up, like into a Dropbox or something like that, where those of you who are watching on the stream can get access to these materials. But you know, sometimes I'm developing them right before class starts or in the middle of the night, and so I don't always get around to doing that. So I need to think about how to do that in a way that I can maintain and not like forget to do it, not forget to update it when I do make changes. Anyway, yeah, have a great day, and I'll see you either tomorrow or on Monday. Glad you were able to join me. Bye-bye.